Hey everyone, let's take a look at number 9 in section 6.4. A little bit different one for shell method here. We're going to use the shell method to find the volume of the solid obtained by rotating the region A. So they give you a figure with regions A and B about x equal 5. Okay. Now the region looks something like this. There's some quadratic function here, which is y equals x squared plus little b. And then you have a shade. I've shaded in region A. Region B is the area underneath this quadratic function, and they have the values of A and B. Now, your values of A and B might be different, and again, you might not have x equal 5. You might have x equal 4 or x equal 6, something different. At any rate, it would be this very similar problem. First of all, my function for mine is y equal x squared plus little b, which is 1, so y equals x squared plus 1. And A, of course, is equal to 2. So let's just, this is going to be x equal 2. This will be by is equal to 1. And when I plug in x equal 2, because we're looking at this region bounded by these two lines, this horizontal and vertical line. So the line x equal 2 here, what's this horizontal line? Well, if I plug in 2 into my function, 2 squared plus 1 gives me 5. So this is y equal 5 here. So we're basically trapped between the curves y equal 5, that line, and the graph of y equal x squared plus 1. So again, this is now x squared plus 1. We'll just go and write it that way. On the interval from 0 to 2. And we're going to rotate that region about the line x equal 5. I haven't quite drawn this to scale. If this is 2, it'll be further over. But the general idea is we're going to rotate this out and then come back in. So we're going to get this three-dimensional solid coming out. What is the volume of that solid? Well, we're going to go an arbitrary distance x from the y-axis here, and we're going to look at this rectangle here. We're going to rotate that up and around the line x equal 5. And when we do so, we get this thin cylindrical shell. Now, the height of our shell, I call that h of x, right, will just be the height of this rectangle. And remember, it's bounded by, this is y equal 5, this line here, and this is y equal x squared plus 1. So it's y equal 5 minus y equal x squared plus 1. So it's 5 minus the quantity x squared plus 1. So be careful, we do need to distribute that through, and I get 4 minus x squared. And just confirm that that gives you the height of this region as x varies from 0 to 2. At 0, notice the height we're between 1 and 5, so the height should be 4. And by the time we get to 2, right, that height is getting smaller and smaller and smaller, going to 0. When I plug in x equals 0 into my formula, what do I get? 4 minus 0 is 4, and that indeed is the height at x equals 0. And as x gets bigger, this height is getting smaller. In fact, when I plug in x equal 2, 4 minus 2 squared is 0, and that height has gone to 0. Now the radius is, this is the x equal 5, right, our axis of rotation. The radius is this distance here from this rectangle all the way to x equal 5. Well, the total distance from the y-axis to here is 5 units, right? This is x equal 5. This is x, right? And we're integrating from 0 to 2 for x. So what's this distance? Well, if this is 5 and this is x, this is what's left over. So this is 5 minus x, right? Is that area there. So if x is equal to 1, then what's the distance? 5 minus 1 is 4, right? It's 4 units till we get to the axis of rotation. So that's what that radius is, 5 minus x. So remember, if we were to snip up this thin shell and spread it out, we'd have a rectangle of height h of x. What would the length be? Well, it's the circumference of the circle, which is 2 pi times the radius. So this would be the area of this shell, essentially, that we're going to then add up from 0 to 2, or integrate, right, from 0 to 2. And so our integral becomes 0 to 2. I pull that 2 pi out. P of x, remember, P of x is 5 minus x, and h of x, 4 minus x squared. So there's the integral we need to evaluate to find the volume of this solid. Okay, so how do we proceed now? Well, I would go ahead and FOIL this out, which is what I did. First, I get that, outer, well, inner rather, I get that, outer, I get that, and then last gives me this. So I pull all that out, and now I find the antiderivative and use the fundamental theorem of calculus part 1 to evaluate this. So the antiderivative hopefully is making sense here. Antiderivative 5x squared is 5/3 x cubed, antiderivative x cubed, and then I plug in 2, I get this, plug in 0, of course you just get 0. So this is it. You can use your calculator maybe to help with this, but to get the exact value, make sure you can do that. Don't forget your pi here. You get 136 thirds times pi, or you can write that as 136 pi over 3, same thing. And that is how you do this one. Kind of an interesting problem here. Okay, I hope this helps.